My name is Don Mercer, and in this video we would like to compare wet basis moistures and dry basis moistures. Financial support for production of this series of video presentations was provided by the Széchenyi Society, founders of the Hungarian programs at the University of Toronto. The Széchenyi Society sponsorship is gratefully acknowledged. I would personally like to thank Dr. Leventi Diashadi, professional engineer and fellow of the International Academy of Food Science and Technology, who is a professor in the Department of Chemical Engineering and Applied Chemistry at the University of Toronto. Dr. Diashadi's considerable efforts in coordinating this project are greatly appreciated. The material in these video presentations is based on an ebook published in November of 2014. Its title is An Introduction to the Dehydration and Drying of Fruits and Vegetables, and it is available on the International Union of Food Science and Technology website, which can be accessed through www.FIAFoST.org. We will begin with a brief introduction and then define both wet basis and dry basis moistures. After comparing wet basis and dry basis moistures, we'll take a look at a popular misconception and then do a sample problem involving water removal. We will finish up with some summary comments. In a previous video, we took a brief look at moisture calculations involving wet basis moistures, expressed as a % water of the total weight of the material. Wet basis moistures can be very deceptive, as we shall soon see. Wet basis moistures are defined as a % on a weight basis. So the % wet basis is equal to the weight of the water in the sample divided by the total weight of the sample, and this decimal fraction is then multiplied by 100%. Before we can go too much further, we need to introduce a second method of expressing moisture. This is the dry basis moisture, and it expresses the moisture content as the weight of water per unit weight of dry solids. So the dry basis moisture is equal to the weight of water divided by the weight of dry solids, and it will have units of grams of water per gram of dry solids or kilograms of water per kilogram of dry solids. In fact, any dimensionally consistent units of weight will be totally acceptable for expressing dry basis moistures. To convert from wet basis moisture to dry basis moisture, begin by assuming that you have 100 kilograms of the material. Multiply the 100 kilograms by the % wet basis moisture to get the weight of water. Then multiply the 100 kilograms by the % solids to get the weight of solids. Or you can take the 100 kilograms of starting material and subtract the weight of the water to get the weight of the solids. You can then divide the weight of water by the weight of solids to get the dry basis moisture. Let's do an example. What is the dry basis moisture of mangoes having a wet basis moisture content of 85% by weight? We will start with 100 kilograms of mangoes. This starting weight will contain 85 kilograms of water and 15 kilograms of solids. The dry basis moisture will be equal to the weight of the water divided by the weight of solids, which is 85 kilograms of water divided by 15 kilograms of solids, or 5.67 kilograms of water per kilogram of dry solids, which is equivalent to 5.67 grams of water per gram of dry solids. To convert from dry basis moisture to wet basis moisture, we will look at the dry basis moisture and consider what it is telling us. A dry basis moisture of 5.67 grams of water per gram of dry solids, which we had in the case of the mangoes, indicates that you are dealing with 5.67 grams of water and 1 gram of solids. This means that you have a total of 6.67 grams of material, which was obtained by adding the weight of the water and the weight of the solids. And this is a key step. The percent wet basis moisture is equal to the weight of the water divided by the total weight times 100%, and in our case that's 5.67 grams of water divided by 6.67 grams total times 100%, and that gives us 85.0% wet basis moisture, which is the starting basis for the mangoes. In order to compare wet and dry basis moistures, let's draw a graph where we put the wet basis moisture on the vertical axis and the equivalent dry basis moisture on the horizontal axis. When we go to the next slide, notice how the line on the graph is not straight. This tells us that there is not a linear relationship between the wet and dry basis moistures. So here we have the graph with the wet basis moisture as a percent by weight on the vertical axis and the dry basis moisture as grams of water per gram of dry solids on the horizontal axis. And you will notice that there is not a linear relationship between the two values. Now let's do some additions of water to 1 gram of dry solids, and we will do this in steps of 1 gram of water. We will then show these on the graph and explain what we see happening. In this graph, we have taken the lower portion of the graph which you saw several slides ago. It goes from 0 grams of water per gram of dry solids to 7 grams of water per gram of dry solids. At the bottom left-hand corner of the graph, which is the origin, we have 0 grams of water per gram of dry solids, or 0% wet basis moisture. These values are often referred to as being a bone-dry basis. Now what we will do is start with 1 gram of dry solids, to which we will add 1 gram of water. So 1 gram of water per gram of dry solids is equivalent to 50% as a wet basis moisture. And the change in the wet basis moisture we get through the addition of 1 gram of water to a gram of dry solids is equal to 50%. Now let's add another gram of water to the gram of dry solids so that we have 2 grams of water per gram of dry solids, and this is equivalent to 66.7% as a wet basis moisture. The change that we get in the wet basis moisture for this step is 16.7%. Adding a 1/3 gram of water per gram of dry solids, we get 75% as the wet basis moisture, and this increment gives us a change in the wet basis moisture of 8.3%. We will finish up by adding a 1/4 gram of water per gram of dry solids, which is equivalent to 80% on a wet basis, and that gives us a change in moisture of only 5.0%. So as you can see, even though we have done equal increments of moisture on a dry basis, the changes in the wet basis moisture are not equal. In fact, they decrease quite rapidly as we go up in wet basis moistures. If you are really serious about drying and need to do calculations, you should be working with dry basis moistures. Dry basis moistures are based on a unit weight of dry material and do not introduce the problems associated with wet basis moistures. A closer look at the definition of wet basis moistures will show us why they are not linear in relationship to the dry basis moistures. We will start by repeating the equation for wet basis moistures, and of course that's equal to the weight of the water in the sample divided by the total weight of the sample times 100%. So we will consider 100 kilograms of tomatoes with a moisture content of 95% on a wet basis as we examine what's going on. The weight of the water will be 100 kilograms times 95%, which is 95 kilograms. The weight of the solids can be found by taking the initial weight of the material and subtracting the weight of the water, which gives us 5 kilograms of solids. The percent wet basis moisture was defined as the weight of water, 95 kilograms, divided by the total weight, which is 100 kilograms, times 100%, and that gives us 95% moisture on a wet basis. The dry basis moisture is equal to the weight of the water, 95 kilograms, divided by the weight of the dry solids, which is 5 kilograms, and this gives us a dry basis moisture of 19.0 kilograms of water per kilogram of dry solids. What I would like you to notice is that in the numerator of this expression, we have 95 kilograms of water divided by 100 kilograms of total material. In the dry basis moisture, we have 5 kilograms of solids, and these values will be important in a subsequent calculation. Now we will remove 50 kilograms of water from the batch of tomatoes in a drying operation. The total weight of the batch will now be 100 kilograms minus the 50 kilograms of water that were removed, for a total weight of 50 kilograms. The weight of the water will be the original 95 kilograms minus the 50 kilograms that were removed in drying, which leaves 45 kilograms of water. And the weight of the solids will remain constant at 5 kilograms since no solids have been removed. Now we will calculate the percent wet basis moisture after the water has been removed. 45 kilograms of water divided by 50 kilograms total times 100% gives us 90% as the wet basis moisture. The dry basis moisture is 45 kilograms of water divided by the 5 kilograms of dry solids, or 9.0 kilograms of water per kilogram of dry solids. Now let's take a look at these values that we highlighted in squares a few slides ago. We now have 45 kilograms of water and 50 kilograms of total weight. In the denominator of the dry basis moisture equation, we still have a constant value of 5 kilograms of solids. You will notice in the wet basis moisture calculation that both the numerator and the denominator are changing, while in the dry basis moisture calculation, it's only the numerator that's changing and the denominator remains the same. So once again, notice how both the numerator and denominator change in the case of the wet basis moisture when the amount of water is changed. The denominator for the dry basis moisture stays constant when the amount of water is changed because it is dry solids and they are constant throughout the drying operation. There is a popular misconception that if you double the wet basis moisture, you will double the dry basis moisture content as well. This really isn't correct. So let's take a wet basis moisture content of 35% and then double it to 70%. We'll base this comparison on 100 kilograms of starting material with an initial moisture content of 35% on a wet basis. The weight of the water present will be 35 kilograms. The weight of the solids will be 100 kilograms minus the weight of the water, which leaves us with 65 kilograms of solids. The dry basis moisture content will be 35 kilograms of water per 65 kilograms of solids, which gives us 0.54 kilograms of water per kilogram of dry solids. Now we'll take 100 kilograms of material at 70% wet basis moisture. The weight of the water will be 70 kilograms and the weight of the solids will be 30 kilograms. This gives us a dry basis moisture of 70 kilograms of water divided by 30 kilograms of solids, or 2.33 kilograms of water per kilogram of dry solids. So comparing these two values, at 35% wet basis moisture, we have a dry basis moisture of 0.54 kilograms of water per kilogram of dry solids. And when we go to 70% wet basis moisture, the dry basis moisture is 2.33 kilograms of water per kilogram of dry solids. So although the wet basis moisture is doubled, the dry basis moisture certainly is not. In fact, it's greater than 4.3 times the dry basis moisture content at 35% wet basis moisture. The problem of working with wet basis moistures is particularly obvious when we consider moisture differences. We're going to consider 100 kilograms of apples at 84% moisture being dried to 14% wet basis moisture. Then we will compare this to drying 100 kilograms of potatoes from 78% moisture to 8% moisture. In the case of the apples, the change in moisture is 70%. That is 84% initial moisture minus 14% final moisture. In the case of the potatoes, the change in moisture is also 70%. This is going from an initial moisture content of 78% down to a final moisture content of 8%. If the moisture difference is the same, then shouldn't we have to remove the same amount of moisture in each case? We shall now see if that's correct. We do not really need a diagram for this problem, so we'll start by calculating the initial water and solids content for the fresh apples and then find the water content of the dried apples. Then we can calculate the amount of water removed. The weight of the water in the fresh apples is equal to the weight of the apples times the moisture content as a decimal fraction, and this gives us 84 kilograms. The weight of solids in the fresh apples is the weight of the apples times the solids content as a decimal fraction, and that equals 16 kilograms. Or you could have taken the 100 kilograms minus the 84 kilograms of water and also obtained a weight of solids in the fresh apples of 16 kilograms. The weight of the solids at the start will be equal to the weight of solids in the final product in most drying processes. This assumes that there are no solids lost in the drying operation, which is usually a safe assumption. So the percent solids in the product will be 100% minus the percent water in the product, and that gives us 86% solids in the dried apples. We're going to let the weight of the dried apples be X kilograms, since we don't have an actual weight for them. 86% of X, or 0.86X, will be equal to the weight of solids in the product, and this is equal to 16 kilograms. We can then write down 0.86X equals 16 kilograms, which we can then use to solve for X, where X is 16 kilograms divided by 0.86, and that's equal to 18.6 kilograms. The weight of water in the product will be equal to the weight of the product, 18.6 kilograms, minus the weight of solids, 16.0 kilograms, and that's 2.6 kilograms of water in the product. The weight of water removed from the apples will be equal to the weight of the water in the fresh apples minus the weight of water in the dried apples, and substituting the corresponding values gives us 81.4 kilograms of water that must be removed to dry the apples. Now we can deal with the potatoes. We're going to start by calculating the initial water and solids content for the fresh potatoes and then find the water content of the dried potatoes. Once we've done that, we can calculate the amount of water that will be removed. The weight of water in the fresh potatoes will be equal to 78 kilograms, and the weight of solids in the fresh potatoes will be equal to 22 kilograms. Once again, the weight of solids at the start will equal the weight of solids in the final product. And we need the percent solids in the product, which equals a 100% minus the percent water. That's equal to 100% minus 8%, or 92% solids in the final product. In this case, we will let the weight of the dried potatoes be y kilograms. So 0.92y, which is 92% of y, will equal the weight of solids in the product, and we know that's equal to 22 kilograms. So 0.92y equals 22 kilograms, and we can rearrange this to solve for y, and we find that y is equal to 23.9 kilograms. So the weight of water in the product will be equal to the weight of the product, 23.9 kilograms, minus the weight of solids, 22.0 kilograms, which means that we have 1.9 kilograms of water in the final product. The weight of water removed from the potatoes will be the weight of the water in the fresh potatoes minus the weight of water in the dried potatoes, for which we get the value 76.1 kilograms. So 76.1 kilograms of water must be removed to dry this batch of potatoes. Both the apples and the potatoes had a moisture change of 70% on a wet basis. Both had a starting weight of 100 kilograms. But we had to remove 81.4 kilograms of water from the apples to get a 70% moisture change, while we had to remove 76.1 kilograms of water from the potatoes to get a 70% moisture change. So the bottom line is that you cannot compare the differences in wet basis moisture content between two samples as we have shown here. This is because wet basis moistures are not linear. We will continue to stress this point in other video presentations. In summary then, this video has provided a brief introduction into the topic of wet and dry basis moistures. A future video will provide more insight into calculations involving wet and dry basis moistures. Please do not underestimate the importance of understanding the difference between the two moisture values and the need to be able to convert from one form to the other. Thank you very much.